All right, so our final and probably most interesting piece of information is the coupling patterns of our peaks, right? So before we said this corresponded to some hydrogens, and we can see it looks different, right? This peak is really kind of 3 peaks in one, whereas this one is even more peaks than 3. And then this one is also kind of 3 peaks in one. And then if we go over to the right here, again, we see a whole bunch of peaks corresponding to actually just 1 peak. And then we see this kind of 2 peaks over here. And so let's figure out what that means. And so this is called the coupling, or the multiplicity is another name for it. And what this tells us is about neighboring protons. So if you have a proton and you have a neighboring proton, they will split one another or split their peaks. And so the most important piece of information that you want to know is that this only works from 3 bonds away, or at least most of the time, right? So if you have a hydrogen that's on a carbon, that's on another carbon that has a hydrogen, right? If we think about the number of bonds away, that's 1, 2, 3 bonds away. And so these two will couple with one another and they will split their peaks. And so let's take a look at how this works. So if we have no neighboring hydrogens, maybe something like a CH3 that's connected to a carbon that is connected to then 3 other non-hydrogens, right? Maybe something like a tert-butyl type of group. What we'll see is this peak won't be split at all. And so you'll just see 1 peak. We call this a singlet because it's 1 single peak. If you have 1 neighbor, then maybe you have something like a methyl group, and then there's a hydrogen here, and then there's some other kind of carbon here, or some other group here and here, right, with no hydrogens on it, right? This will be 3 bonds away as well, right? If you think about the H's here, 1 bond, 2 bond, 3 bonds away. And so now these 3 H's that we're looking at over here will be split by this other H. And so this other H that I'll color in purple here can either be pointing up or pointing down. And so it'll evenly split the peak into 2 evenly sized peaks. And so we call this a doublet, right? Because there's 2 peaks there. What if we have 2 neighboring hydrogens? And so we have some kind of CH3 here, and now we have 2 H's on this carbon, right? So these 3 H's will be split by these 2 H's in blue. Make it purple, stay consistent. And so we can think about how these H's can be pointing up or down, right? They can either both be pointing up, they can both be pointing down, or one can be up, one can be down. But if you think about the ways you can construct this, you could have the first one be up and the second one be down, or you could have the first one be down and then the second one be up. And so if we think about it, that's 3 distinct peaks where the center one is twice the size of the surrounding ones. And so that's what you would see, right? You would see 3 peaks where the middle one is about twice the size of the 2 surrounding ones. And this is called a triplet peak, right? Because there's 3 of them. Then what if we have 3 neighboring hydrogens? This time, let's take a look at this hydrogen, which is being split by all 3 of these hydrogens here. And so if we think about the way these hydrogens can be organized, they can all be down, they can all be up, or we could have 2 down, 1 up, or 2 up, 1 down, right? And then there's multiple ways to organize this system, right? You could have the first 2 be down and then 1 up, or the center one could be the one that's up, or the first one could be the one that's up. So there's 3 ways to organize that. And then same thing over here. Maybe the first one's down, or maybe the second one's down, right? But you can see they all have the same kind of macro state, if you will. And so if you think about the peaks here, you'll get 4 of them. where these two middle ones are approximately 3 times the size of the other ones, and this is called a quartet. And so you can see, depending on the splitting of our compounds, we'll get information about how many surrounding hydrogens we have. And so this is what's known as the N+1 rule. And so what this says is that the hydrogen will split into N+1 peaks, where N is the neighboring hydrogens. Right. So for example, if you have 0 neighbors over here, you will then be a singlet. If you have 1 neighbor, you will show up as a doublet, 2 as a triplet, 3 as a quartet, 4 as a quintet, 5 as a sextet, and then 7 as a septet, right? But you see they all kind of have this organization where they're all kind of pyramiding up to the top. So some other things to note is that hydrogens don't split if they're the same or if they are chemically equivalent. So for example, in our cyclohexane, right, all of these hydrogens were said they're all the same. And so you'll only have 1 singlet to represent them all, right? They don't couple with one another if they're the same. They will split if they are diastereotopic. So for example, something like an alkene, if we have HC, HA, and then HB, right, we're going to have splitting here because these 2 hydrogens are diastereotopic. And they can split even though they're only 2 bonds away. So it's, I guess, 2 to 3 bonds away, really. And then these 2 will also split as well, right? So that one will split with this hydrogen as well. And so if you take a look at a compound, you should be able to figure out its splitting pattern. So let's go ahead and take a look at this type of compound. And then we want to identify all the splitting patterns of all of our hydrogens. So if we start over to the left, right, we have these CH3, CH3, CH3. They're all part of this tert-butyl group. And so they're all chemically equivalent. And so they won't split one another. And then if we think about any hydrogens, neighboring hydrogens, there are no neighboring hydrogens on this neighboring carbon. And so this would be a singlet. So you'd see a big peak and it would integrate to 9 hydrogens, which represent those, right? There's no hydrogens here, so we don't worry about that at all. There's a hydrogen over here. And then 3 hydrogens over here that are equivalent, right? So if we take a look at this hydrogen, it has 3 neighbors. And so that will split into a quartet that will integrate to 1H. If we think about these 3 hydrogens here, they all have 1 different neighbor, right? They're not going to split each other because they're chemically equivalent, but they have 1 different neighbor. And so that'll show up as a doublet, which should integrate to 3 hydrogens. If we move over here, we have this hydrogen. And then we have these 3 hydrogens over here. As well as these 3 equivalent hydrogens as well, right? On this isopropyl group, all these hydrogens are going to be the same. And so if we think about these yellow hydrogens, they have 1 neighbor, and so they'll show up as a doublet that integrates to 6 different hydrogens. And then we have this hydrogen over here. It has 6 neighbors, and so it'll split up into 7 peaks or a septet. See, I'm not going to draw that. but just say septet, that integrates to one hydrogen, right? And so you can predict the NMR spectra of most simple compounds by thinking about their splitting patterns, thinking about which hydrogens are chemically equivalent, and then we could also think about where they'll be in our spectra, right? The closer they are to this carbonyl group, the further de-shielded they will be. The further away they are from that carbonyl group, the further to the right on the spectrum they'll show up. So let's go back to our example in the beginning, right? Remember we said that this was 1-chloropropane. And so we have these 3 hydrogens, or these 2 hydrogens, these 2, and then these 2. And so if we think about the neighboring hydrogens next to these 2, we only have these 2. And so that should end up being a triplet. And if we zoom in on the corresponding peak right here, we see that it is indeed a triplet. Next up, we have these 2 hydrogens right here. They have 5 neighbors, and so they should have 6 peaks. And so if you count these right here, there's 1, 2, 3, 4, 5, 6, right? A sextet. And so that looks good right there, right? Those peaks correspond to those right there. And then finally, we take a look at these 2. They have, or these 3 protons, they have 2 neighbors. And so n+1 states that it'll be a triplet. And if you check out this one, right, 1, 2, 3, that is indeed a triplet. And then over here, we said that this was 2-chloropropane. We have this hydrogen over here. And then the other 6 are equivalent. We first take a look at these 6 equivalent hydrogens. They have 1 differing neighbor, and so n+1 says it should be a doublet. And so if you look at it here, you've got 2 peaks right here. You've got a doublet, and so that corresponds well. And then if you take a look at this other hydrogen, it has 6 neighbors, so it should be split by n+1 peaks, and so it should have 7 peaks here. And so these are kind of hard to see, but there are these small ones to the left and right. So 1, 2, 3, 4, 5, 6, 7. And so by combining these 4 pieces of information, right, the number of peaks, the location of the peak, the integration of the peak, and then finally the coupling of the peaks, you can figure out the structure of most organic compounds.